Hi, my name is George Hume, and my primary responsibility on Project Pegasus was the landscape, which I took over from Ian after his initial setup. My responsibilities included setting up the pipeline between Houdini and Unreal Engine, detailing the terrain, texturing it, setting up paths on the terrain, scattering foliage, and doing sort of the technical setup inside of Unreal, such as specifying the settings of the terrain and setting up the landscape material. Now, when we set out to create the environment for Project Pegasus, we had a few requirements of the landscape. We wanted there to be a lot of variety. We wanted to reach a very high degree of visual fidelity, and we wanted the terrain to look good from all distances. In addition to that, we wanted to be able to support manual and procedural editing, have the workflow be non-destructive, and be able to support multiple collaborators. So essentially trying to replicate all of the constraints and requirements that we'll be seeing sort of in AAA development pipelines for creating open worlds. So to begin with, I'm going to focus in on these last three since they're sort of the driest part, and then we'll move on to the more pretty and interesting arty stuff. So to begin with, we're going to talk about the pipeline. We made use of world partition, edit layers inside of Unreal, and I'm going to talk to you as well about our caching practices and the way in which we supported a bi-directional workflow between Houdini and Unreal Engine, meaning having sort of changes in one environment reflected inside of the other one, which will allow multiple artists to work together to produce the end result. World partition is a feature of Unreal Engine 5 that automatically dices up and slices up the terrains that you import if you enable it. And it was really essential for creating sort of the giant open world terrain that we wanted to create. Additionally, it means that you have this feature toggled on called one file per actor, which makes it easier for multiple artists to collaborate inside of the Unreal Engine on the same map at the same time. World partition really just works. There's no need to do any specific kind of setup, although if you're working with Houdini, you do have attributes that you can set on your terrain geometry when you export it to disk, and then when you load it into Unreal, you're able to configure certain settings that relate to world partition. We didn't bother doing that, we just used the default settings. Edit layers are a feature of Unreal that allow you to basically have this layer stack where you have different height information contained within different layers, and you can choose how they're blended together and what order they get blended together in. And this is really great because this is what allows us to do the non-destructive editing of the terrain, where you maybe have your source ground truth terrain, and then you sort of blend in these different layers of detail without them sort of overwriting the contents of another layer. So again, this is great for non-destructive workflow and for collaboration. So we made use of this feature. And again, Houdini has great support for this out of the box. So you have attributes that you can set on your terrain geometry when you export it to disk. And then when it gets loaded into Unreal, if you have these attributes set, you'll be able to decide which layer you want to update on the terrain or read from. So this just works really well. It's very seamless and it's very, very quick as well. All right. So now the probably most boring part for most of you, they're going to talk about the caching practices and how we got this kind of bi-directional workflow going. So essentially what I mean by caching practices is we didn't want to just work with Houdini Engine inside of Unreal. We wanted to be able to work both in the Houdini environment and inside of Unreal, so sort of independently of each other and benefit really from the strengths of both programs fully. So the way in which we did this is we set up an external cache on disk, and you can see that we have these three files here, the source, manual, and procedural detail. And basically each of these represents one of those edit layers inside of Unreal. And when we have a change made inside of one of those programs, we'll export it to disk, and then we'll be able to see it inside of the other one. So we built some digital assets to help with that. We've got the load landscape digital asset and the cache landscape digital asset, so they should be fairly self-explanatory. These run inside of the Houdini environment, and they also run inside of Unreal as Houdini digital assets, where you have a variety of settings relating to which layers you want to load or save to disk. So this was really very simple and a very quick way of kind of working. And it meant that we had one source of ground truth that always lived on disk that multiple artists could reference and read from. So that's basically what this diagram is trying to explain or visualize. And you can see that we've got that on disk cache there, and those three files, source, manual edits, and procedural detail. And this diagram is basically just trying to show the flow of information. So we have our incoming height field, which was our starting point. And then that goes for a procedural detailing phase and into Unreal. And any manual edits we make inside of Unreal go back to the Houdini environment so that the procedural detail can then be aware of it. And it's sort of this iterative feedback loop that ensures you've always got the latest state in both programs. So that's how we sort of supported multiple users and also, having that kind of non-destructive workflow and having that bidirectional relationship. So that was all the dry stuff out of the way. Now we can talk about the sort of fun, pretty, arty stuff. And I'm going to start off by talking a little bit about the materials workflow that we built for Project Pegasus. This is sort of really how we detailed and textured the terrain to sort of a higher degree of fidelity, as well as the authoring of these global color maps. So materials workflow, I'm not talking about Unreal materials, although we will get to that in a bit. I'm actually talking about the use of materials directly inside of Houdini to add detail and color to the terrain. So we made use of scan-based detail to take the terrain that we see on the left here, and sort of using masks inside of Houdini, we were able to decide where to apply the detail from various different scans to add this extra layer of fidelity. And just a little bit of by way of explanation here, we obviously have really great tools for sort of sculpting those larger features and forms on the terrain, the erosion, simulating sandfall, deposit, sediment transfer, and all of that kind of thing. But what a lot of terrain tools actually really lack is the kind of tools that allow you to sort of work in extra details on the more sort of micro level. So that's why we took advantage of scans, because you're really able to inject an extra level of a really rich detail in that kind of sub 10 meters level of terrain scale, which we felt really added a lot more on top. And we did this with our custom-built Pegasus height field material node. And what the Pegasus height field material node allows you to do is to take a mask. So you mask a certain feature of the terrain, maybe the slopes, and then essentially you set up this height field material with all of the channels of a material, maybe from Megascans, maybe from somewhere else. And so basically we have this holistic material development process, much like you'd find in a tool like Substance Designer, where you're able to sort of update the color and the roughness and the height simultaneously, just as if it was a material, but in the context of landscapes. So then we basically repeat this process. We stack loads of these nodes together, each with their own masks coming in from outside somewhere. And we're able to decide where we want the grass materials to get placed, where we want the cliffs, the gravel, the sand, the paths. And all of these materials are being blended together to modify not just the color, to author the global color texture that we see there, but also to sort of displace it and add that rich topological detail that I mentioned previously. And here you can see the actual graph that if you decide to follow along with the sort of multi-part series that I've been developing for Project Pegasus, showing you how we built the terrain. This is the actual graph that we're going to build together, and you can see how those layers get blended together to produce the final result. So yeah, that's what that looks like. And here it is running inside of Unreal with the material. So we'll get to this a little bit later on. The height field material node is just one node in a suite of tools that allow you to sort of manipulate and edit the color of the terrain. So we've also built a couple of basic tint functions, power operations, change the ability to change the color space and remap and blur the color. So this is a kind of growing library of nodes that you can think of as basic image manipulation functions that works directly on height fields. So it's quite a nice toolkit, and I definitely enjoyed working with it. I'm excited to see other people maybe sort of using these tools and seeing what they come up with. Okay, so we've talked about the global colors and the materials workflow, and really the goal with all of this toolkit here was to make sure that the terrain works at all distances. So we're not just relying on detailed textures up close, but we're also authoring a global color map. We don't just have large scale terrain features, but we also have some smaller, closer up ones. So that was really built to sort of try and get to this goal, though of course getting high visual fidelity and variety was also a part of that. In addition, to really push that level of visual fidelity and variety a bit further, I'm going to talk to you a little bit about the kind of workflow that we used to add the tiling details, the tiling materials to our terrain. And the way that we did this was through the use of an ID map, which we used instead of weight maps. So first of all, I'm going to talk to you a little bit about how traditionally we handle landscape materials inside of Unreal. Traditionally, if you want to assign a material to a portion of the terrain in Unreal Engine, then you'll create a weight map, which is a grayscale image which defines the strength of one material in a particular location on the landscape. And you'll use a bunch of these to define the distribution of the different materials across your terrain. So an ID map essentially what we're trying to do here is, instead of having one grayscale image per layer, we just have one single grayscale image that defines the distribution of all of the layers across the terrain. And you can see here that in Unreal, we're just sort of visualizing each of those different layers contained in the ID map as a different color on the landscape. And here, if we've sort of zoomed into the terrain, you can see the individual values, or the indices that are being extracted from that ID map. So we've got a region that has a value of 1, value of 5, and a value of 4. And we can use these indices to essentially assign a different material to a different part of the terrain. And this is really how we approach trying to add a lot of variety to our terrain. Why couldn't we just use weight maps? Well, I'll talk about that now. So when you want to have a high degree of variety, then that means you want to have a lot of layers that you're able to support on the terrain. So, it's not enough just to have grass and stone and gravel and, 3 or 4 different layers. You really want to be having like 10, 15, maybe even 20 or more individual materials that you're able to apply to your terrain. And the problem with weight maps is that this means that you're going to need to have a grayscale image that defines the distribution of each of those individual 20 layers. So you have one weight map per layer. With Pegasus, with the ID map, we just have one ID map total, regardless of the layer count. So essentially, we're able to avoid having a memory cost that's tied to the number of layers. We just have a fixed memory cost with that one ID map. And additionally, we also don't have to worry about sending backwards and forwards between Houdini and Unreal all of these individual weight maps. We just send backwards and forwards one. Now, what's the downside of this approach? Well, if we zoom in really close, you can maybe guess, and that is that we have really harshly defined boundaries between the different layers. They're all just solid values in the pixels. There's no blending. And what that would look like if we naively applied it to the terrain and just used the raw indices is something like this, where you can see very clear pixelated pattern. And in a little bit, I'm going to talk about the techniques that we use to avoid our terrains looking like this and looking a little bit more like this. But before we get to that, I'm just going to talk about the tools that allowed us to develop this ID map inside of Houdini. And it's quite simple. We define sort of a set of layers. So we're instructing Houdini what the different IDs in our ID map relate to. So this is just really helping us to set up a nice user experience where you name your layer and you give it a color. And you can work interactively in the viewport. And then you use a mask. You tell the ID map which layer you want to inject into it and which mask you're going to use. And then that sort of injects that information into one of those ID maps. And we also have the ability to extract sort of a mask from the ID. So you can say, okay, I want to see what the contents of the grass 2 ID looks like, and then you've got this mask back out of it. So you can see that really they're just masks, but they're all contained within a single image. And then the workflow is, after you've set up the layers that you want using the ID map layers node, you basically string together a bunch of height field layers to ID nodes, and that allows you to fill out the different values of the ID map. And you can see that every layer is essentially its own sort of grayscale value there contained within the ID map. So we're just reusing the masks that we created during the height field materials tooling process. So it's sort of really nice toolkit that all works together to allow you to sort of embrace this new workflow inside of Houdini and Unreal for texturing terrains. So I mentioned before that we had to come up with some sort of tools or techniques inside of Unreal to be able to read the ID map and to get it to look a little bit better. So I'm going to start talking to you about the material. And I'm also going to talk to you a little bit about texture arrays. So the traditional paradigm inside of Unreal is that you have a bunch of weight maps, and then you have sort of a material definition. So in this case, we've got our grass layer. You sample the weight map for the grass layer, and then you maybe sample sort of all the textures for the rock layer, and then you have the weight map for that, and you blend all of these different layers together, and you can think of each individual layer as a whole material in of itself. So this is also problematic from the perspective of memory and shader complexity, because not only do you have sort of n weight maps, that is weight maps times the number of layers, you also have number of texture samples times the number of layers. And since you tend to use more than one texture to define a material, you have the color, the normal, and then maybe some masks, you're going to end up with this sort of multiplying together to further increase the amount of sort of memory that's being used, but also just increasing the shader complexity sort of linearly as you increase the number of layers. And this is again sort of a limiting factor that you have when you're working with traditional Unreal landscapes. So this would have really prevented us from getting that sort of higher degree of variety that we wanted to be able to achieve. So we used a new feature, or a newish feature inside of Unreal Engine, which is texture arrays. And what texture arrays are they're sort of a vehicle that allow you to sort of plug in a whole set of textures into one asset, and then you can sample that texture array inside of the material. And by providing the texture array with an index, you're able to sort of apply the textures that are contained within that index to that portion of the terrain. So you can see here we've got this sort of drop down with a bunch of indices, and for each index of the array we're adding a new tiling texture. And of course I've used the word index a bunch of times now, so we're just feeding into this texture array the indices that we get from our ID map, and that's what we can see here. Every color is its own ID, and then we're extracting from that texture array a different tiling texture according to which ID is currently on that part of the landscape. Now, I also mentioned previously, and it's quite clear to see in that last image, that if you just do that naively, you get this kind of sort of bit-like appearance where you can clearly see the pixels. And the way we get around that is we just sample the texture array 4 times with a slightly offset sample from the ID map. So sort of you can imagine this as for every pixel on the terrain, we're getting the top, left, right, and bottom sort of value from the ID map, and then we're going to just blend all 4 of those samples to produce the final result. And that gives you a smoothly interpolated material on your terrain that looks just like this. So that's how we get around that. And what we get as a sort of a benefit from that is, whereas before we have an increasing number of sort of weight maps, we have an increasing number of texture samples and an increasing number of amount of shader complexity. With the Pegasus material, you have just one ID map. You have maybe, let's say you're using color, normal, and masks as your textures. You sample each one 4 times. You have just a total of 12 texture samples, regardless of the layer count. And you also have that fixed shader instruction count, which doesn't increase as you increase the number of layers. So all around, this approach is much better when you're trying to deal with extremely sort of large open worlds and you want to be able to support a high amount of variety there. Okay, so onto the kind of more detailing of the terrain, the more arty stuff again, after we took a bit of a detour into the sort of technical territory a bit. So this is basically how we approached creating sort of paths, tracks, and trails across our terrain. We built a node called height field paths, and the height field paths node takes in a height field as an input, some waypoints, and then it will create some paths across the terrain. Inside of the height field paths node, you have some settings, and these are essentially the costs of traversing different regions of the terrain. And by default, there's going to be a cost associated with sort of going uphill. That's what this rate of change of height cost is here. And that's the kind of cost that causes paths to sort of wiggle up slopes. Then you don't really want paths to be able to traverse the steepest cliffs. So we just have a raw cost associated with traversing slopes of varying steepness levels. And then that would just kind of be basic. So to take it one step further, we also have the ability to blend in any other kind of masks we want. So in this case, I'm using the occlusion of the terrain, which really picks out sort of the ridges or the valleys and causes the paths to prefer to move either along the ridge lines or in the sort of the gullies and furrows of the terrain. So you can see we've got this visualized here with 3 different colors. These sort of green paths prefer moving along the sort of ridge lines and more exposed areas, whereas the red ones are sort of moving through those valleys and furrows a little bit more. So you can really try to sort of art direct and describe the behavior of whatever creatures have been leaving these paths across the terrain. We also, of course, have the ability to sort of set waypoints. So here you can see there's a waypoint on top of the mountain, and then with the costs that we've created inside of the height field paths node, we're able to define the kind of behavior of that path as it sort of creeps up the terrain. And here again is another example of that. And here's the same thing, but with just a few more paths. So you can see how you get really interesting looking paths across the terrain with some very simple controls there. And the benefit of this is that we're able to sort of add a lot of interesting sculpted detail to the terrain that it would be really hard to either add this manually or to sort of manually draw these lines. And there's no sort of simulation process that will do this for you. So the height field paths node really allows you to create this extra layer of detail, and not just for the sort of main paths that the humans are using, but also sort of to describe things like animal trails, which can then be used to change what vegetation would spawn, how bare the tracks are, and how short the grass is, etc. So we take that through into the color layer, we take that through into the ID map, send it all over to Unreal, set up a new set of textures in the texture array, and then we have the paths described and represented inside of Unreal there, adding a lot of visual interest to the terrain. And this was really helping to help us push the high visual fidelity. So some other things that we did was, of course, adding props to the terrain. So the distribution of trees and woodlands. The way we did this, so it was really fairly straightforward. We just mask certain regions of the terrain. We scatter some points in them. And then to take it one step further, we created this node called height field advect points. And the most simple way of thinking of this is it allows you to roll points up or down the terrain. So this is what the flow map looks like if you roll those points up and leave a trail behind them. And this is what it looks like if you roll them down. You could imagine that if you roll them up, you're going to sort of get the rocky ridges. And if you roll them down, you're going to sort of get the scree and boulders that have fallen down the hill. And in the context of vegetation, what can be really interesting is to actually, instead of using the slope, you use, again, the occlusion. So you can roll points towards or away from occluded areas, which sort of simulates or emulates the way in which different types of vegetation might have a preference for different levels of exposure or different levels of moisture in the soil. So this is a really nice and interactive way to sort of art direct those points after the fact. And here you can see that we've just imported those points into Houdini using a raw kind of import tool that Houdini ships with. And you just provide a reference to the asset that you want to scatter, and it just spawns it straight there. You know, there's no heavy information or data being sent from one program to the other. This is pretty much instantaneous. You drag in the scatter and it's populated with the trees. So really great work by the Houdini engine team to get that working as well as it does. And now I'm going to talk a little bit about the scattering of the smaller foliage and vegetation, because we don't want to be sending the millions and millions of points from Houdini to Unreal that would describe every blade of grass, of course. And to do that, we just used the native landscape grass system. Inside of our material, we have the ability to define which grass type we want to associate with which material layer. And those grass types are defined by grass type assets. And you just read that into the master material, masking out the different IDs of the ID map. So basically working in a very similar way to the way that we sort of sample the texture array and grab a specific index from there. In this case, we're just grabbing the index of the grass type that we want to assign to a different region of the terrain. To add new grass types, it's as simple as going back into Houdini, creating some new masks, maybe sort of modulating the global color and ID map, and then bringing those back into Unreal and setting up that new grass type selection there. All right, and finally, and possibly one of the more exciting things for a few people, I'm going to talk a little bit about Nanite terrains and displacement and tessellation, which are all new features, somewhat experimental in Unreal 5.3. And I can definitely say, despite the experimental nature of these tools, they work very well out of the box. You may be able to see a slight seam along the terrain there. We did actually end up fixing that quite simply. So if you follow my sort of mainline tutorial series on setting up this terrain, then I'll discuss the ways that I address that. But you can see just how much detail gets added to the terrain through this runtime tessellation and displacement feature. In order to get this working, you just need to turn on Nanite on your terrain by toggling a switch and hitting build data, and also going to the default engine .ini file in your project location and adding these two lines to allow tessellation as a feature. And I'm sure that we'll be seeing this becoming more of a first party or more of a well-supported feature in the future. So that's just the setup inside of Unreal there. And now I'm going to basically show you what it looked like previously to turning on the displacement. You can see it sort of looks quite last gen, a little bit low res. And then if we just fade in the tessellation there, it makes a huge difference. So can't overstate how great it is to have this feature back inside of Unreal Engine. Of course, this doesn't come for free, and we noticed a pretty sizable performance cost from turning this back on. But that being said, I think that the cost in this case was benefit, since we're making a kind of showcase project and we want things to look as good as possible. So yeah, that's the difference there from left to right. That's the end of my talk. At least for now, I'll be back a little bit later to talk about the Flora tools that we've been prototyping, which I'm really excited to share with you. And you've got a ton of other interesting stuff coming up from the other artists later on in this presentation. So thanks for watching, and you'll hear from me again later. Bye for now.